that takes us to our fourth page of notes and what happens with when plates converge. So in this example, we're looking at an ocean-ocean convergence boundary. And there are several features that I want to point out here. The overall features I want you to associate with an ocean-ocean convergent boundary are the volcanic island arc and the subduction zone. Okay, so apart from that, breaking down everything that's going on here, first we have the trench. The trench forms where the downgoing plate gets flexed downward, where that subducting plate starts to bend and dive down into the earth. The accretionary prism forms when some material gets scraped off from the plate that is subducting. So basically it's a buildup of debris from those two huge plates grinding against one another and scraping off material. As that plate subducts and dives down into the earth, it's under higher pressure, it's under higher temperature, and so the slab begins to release water. This water is coming from within the mineral structure. So when these oceanic crustal rocks are forming at the mid-ocean ridge, there's water cycling through that system, and it becomes bound up in their chemical structure. So if I had a piece of oceanic crust in my hand right now, it would not be dripping with water, but it is composed of water in its structure. So as you heat that up, as you squeeze it under these high pressures, it starts to drive off water. So you get chemical reactions on that downgoing slab, releasing water from the oceanic crust. And when you add water to that system, that triggers melting of the mantle. Just like if you were cooking, let's say maybe you're trying to make caramel or something, you're trying to melt sugar. If you just had sugar in a hot pan, it would take you ages to start to melt it, but if you put in a little bit of water, that really gets things going. So in the case of a subduction zone, when water is driven off of that subducting slab, that's really what begins the melting process. So once that melting starts, we're forming magma. The magma is working its way up to the surface, forming volcanoes, and you get eruptions that form a volcanic island arc. And it's forming an arc because the Earth is a sphere. So this plate that's diving down into the Earth is projecting that magma upward onto a sphere. So it ends up arcing and making the semicircle shape. The best example of this is occurring in Japan. Okay, so again, the main features to associate with an ocean-ocean convergent boundary are a subduction zone which forms a volcanic island arc. And what happens when an oceanic plate and a continental plate collide? So again, we're changing the composition of the crust here, and so we're going to end up with slightly different results. The mechanics are pretty much the same, but because the composition is different, the densities are different, the result is not the same. So in this case, we have an oceanic plate subducting below a continental plate. We get that trench again where the subducting plate starts to bend and dive down into the earth. The oceanic plate is always subducted beneath the continental plate because it's more dense, because it's thinner. It's easy for it to give way. So the oceanic plate is pulled down beneath the continent. We get the trench along the continent, and the overlying mantle begins to partially melt. Again, this has to do with water being driven off of that subducting plate, which triggers the melting. And as that magma rises up, it can melt part of the continent. And as I mentioned previously, when you melt the continent, because the continental crust has stronger bonds, you end up with more explosive volcanoes. Things are more dangerous. and you have a thicker magma based on that continental composition. Along with the magma working its way up to the surface, once it erupts, it forms volcanoes, but you also get these long mountain belts along subduction zones at ocean-continent convergent boundaries. Because you're squeezing that continental crust together, it's buckling as these two huge forces are colliding. Our next question is what happens when two continents collide? So we've got a continent-continent convergent boundary here. I apologize, in your notes you have the wrong picture there, so hopefully you can sketch this out. At a continent-continent convergent boundary, as those two huge, equal density, powerful, buoyant continents plow into one another, they buckle and they start to slice off pieces. And so this zone, this area where all of this deformation is occurring, where the pieces are being sliced off, these little arrows represent faults. They're thrust faults. This is called a zone of deformation. So we have a wide zone of deformation. The continental plate is very buoyant. It's not very dense. So it's not able to subduct. You just end up having this large pileup, and as a result of no subduction, you end up with few volcanoes because there's no subducting slab for water to be driven off of to generate the melting, to generate the magma. So very few volcanoes, but in its place, in the place of all volcanic activity, you have these very high elevations. And the best example of this is the Tibetan Plateau in the Himalayas, where India, which was its own continent, collided with the rest of Asia. And so basically you're stacking Asia and India together, and you get extremely high elevations. The highest elevations on the planet occur there because of this type of pileup. Observe the distribution of volcanoes around the Pacific Ring of Fire. What do you think could explain this overall pattern? So take a look at this. Each orange triangle, again, is representing a volcano. And how are they lining up? They seem to line up along the edges of the continents. Not always the case, but in most cases. What do you think is going on here? Okay, so what I want you to do is recall what plate boundaries form volcanoes. And specifically, what plate boundaries form volcanoes on land or are generating new landforms. Okay, so if we look at a side view, this is why there are so many volcanoes located around the Pacific Ocean. The oceanic plates are subducted on both sides. So on the left side of this image, we're looking at what's going on in off the coast of Asia. For example, Japan. We get subduction beneath oceanic plates, and that gives us island arcs. So on the left side of our screen, we're looking at ocean-ocean convergent boundaries that are generating volcanoes which form islands, okay, island arcs. On the other end, we're looking at what's occurring on the western coast of South America and North America. We have the oceanic plate subducting below the continental plate, and so instead of islands, the volcanoes are forming on the continent. So we have mountain belts with volcanoes. Okay, and the example here would be the Andes in South America. The example on the left side of the screen would be Japan or the Philippines. Okay, so I would like for you to be able to explain the Pacific Ring of Fire and why the west and east sides are different. Why do volcanoes on either side of the ocean behave differently? And what's going on in the middle of the Pacific Plate that's driving this subduction? Our next question in your notes is, can oceans disappear over time? And describe how. When we're looking at the mid-ocean ridge and Africa rifting apart from South America, we can see that we can form new oceans. And we know that the Earth is dynamic, it's constantly moving, but we haven't yet talked about an example of oceans disappearing. So that can happen, and that happens in the process of continent-continent convergence. So we start out with subduction of the oceanic part of the plate. This would be like the continental shelf, the shallow area of oceanic crust that is attached to the continent, and that's able to subduct because it is thin and less dense. When it comes in contact with another continent, it doesn't stand a chance. It subducts. Our next image shows us subduction getting closer, bringing the continents closer together. The overriding continent has magmatism while normal subduction is occurring. So what I mean by that is it's releasing water from that subducting slab, which triggers melting, generating magma, and feeding the volcanoes above. And the last step, as we're running out of oceanic crust to subduct, in the final one, we're all out of oceanic crust. Now both continents have been pulled together and continents collide, forming large mountain belts. And again, the Himalayas, where India meets with the rest of Asia, is the best example of this. So the oceanic crust is getting gobbled up in subduction, drawing these two continents together. We've already discussed convergent boundaries and divergent boundaries. Now we're going to talk about transform boundaries. What happens when plates slip past one another? When we're looking at this image, I want to know, where is the transform boundary located in this image? So overall, the arrows are moving away from one another, but at a certain point we have an area that's moving side by side. And that is our transform boundary. So right there at the center, where the plates move horizontally past one another, we're looking at the transform boundary. Transform boundaries link other types of plate boundaries like two spreading centers. That's why mid-ocean ridges have a zigzag pattern, because transform boundaries are linking other boundaries at the mid-ocean ridge. So it's linking together the divergent boundary. And what do transform boundaries tend to connect? Again, divergent boundaries. Describe what is happening along the mid-Atlantic ridge and the types of plate boundaries involved. So overall, the movement at the mid-ocean ridge is apart. We have overall a divergent boundary, but again, in between those divergent boundaries, this zigzag pattern in between the South American plate and the African plate, our divergent boundaries are being linked together with transform boundaries. So the rule of thumb there is, when we have a vertical or a north-south boundary, so you can look at what's being pointed at right here, this vertical boundary, that tells us that the plates are moving apart. So the blue side is moving to the right and the green side is moving to the left. A vertical line means divergent. Okay, if it's a horizontal line, we know that the blue is moving to the right, the green is moving to the left, but they're stacked on top of each other, so that makes it a side-by-side movement. So when you see a horizontal or a east-west boundary, you know you're dealing with a transform boundary. And how is the Mid-Atlantic Ridge affecting the size of the Atlantic Ocean? Well, we know that the Mid-Atlantic Ridge is why we have the Atlantic Ocean in the first place. South America and Africa used to fit together, and it's constantly moving apart, so the Atlantic Ocean is constantly growing. And what would the age of the ocean crust near the Mid-Atlantic Ridge be? We're just asking about relative ages here. So near the center, the rocks are younger. The magma is coming up at that spreading center, cooling off and forming brand new oceanic crust. So those are the youngest rocks right there at the center. What would the age of the crust near the coast of South America and Africa be? Those are further out from the center. So the further away from the ridge you get, the older the rocks are. And why the difference in age between the ridge location and the coastlines? Because the rocks are formed at the ridge and then pushed to the sides over time. All right. Let's take a look at something a little closer to home. Let's describe what's happening off the west coast of the U.S. and Canada. So we can look at our key in the bottom left-hand portion of this map. We have divergent yellow lines, red convergent lines, and green transform boundary. So every type of plate boundary occurs on our west coast. What an active place we are. So that's what's happening. We have transform, convergent, and divergent movement off of our west coast. And how is that affecting the regions? How is this tectonic activity affecting the region? Well, let's take a look. If we head to the bottom right-hand part of this map, we're looking at the San Andreas Fault. So North America is moving to the southeast, and the Pacific Plate is moving to the northwest. The western part of California is actually attached to the Pacific Plate, which is why California has so many earthquakes. So that is how it's affecting us. We get earthquakes along transform boundaries. Let's take a look in the Pacific Northwest. As we follow the San Andreas up, it hits the Cascadia subduction zone. So we have this little plate. The Juan de Fuca plate is subducting below the North American plate. And we know with subduction, water is driven off of the subducting plate, which generates melting. That magma reaches its way toward the surface and erupts as lava out of volcanoes. So this is why Mount St. Helens erupted in the early 80s, and this is why many of the volcanoes in the Pacific Northwest pose a volcanic threat. And further up, we have the Queen Charlotte Fault, and that's the same type of movement as the San Andreas Fault, so generating earthquakes. So back to this question, how is plate tectonics affecting the region? We get earthquakes, we get volcanic eruptions, and it's shaping the landscape. All right, so we've talked about directions that the plates move. Plates move, but why are they moving in the first place? What moves the plates? Overall, the main answer to that question is convection. Hot material rises, cools off, and sinks back down. Okay, but there are two other processes going on here, and we're going to take a look at that. First, we have slab pull. This is the stronger of the two we're going to talk about here. This is the weight, the heft of that subducting plate being dragged down into the earth. Its own weight and the pull of the Earth's gravity dragging it down pulls the rest of it with it. You can think of it like a person trying to drag a car. That plate, as it moves down, is pulling the rest of it with it. That's slab pull. The next is ridge push. So the hot material at the center of a mid-ocean ridge breaks its way up to the surface and pushes the rest of the rocks out of the way. More hot material moves up, pushes the rest out of the way. That's ridge push. So ridge push is the force at a divergent boundary pushing things apart, and slab pull is the force at a subduction zone at a convergent boundary that's dragging the rest of the plate with it. So again, convection in the mantle is the overriding force here, but that contributes to slab pull and ridge push. And not all plates are moving at the same rate. So we're talking about relative plate motion here, and it's represented by arrows. The smaller the arrow, the slower the speed. So plates are moving just centimeters per year, and some move faster than others. So if we're looking for which ones are moving the fastest, we look for the largest arrow moving more than 9 centimeters a year, and the best place to find that is around the Pacific Plate. So we can see where the Pacific Plate meets with the Nazca Plate, where the Pacific Plate meets with the Cocos Plate. We have that high speed where the Pacific Plate meets with the North American Plate up by the Aleutian Islands off of Alaska. So this fast rate of movement at the Pacific Plate is what contributes to the activity at the Pacific Ring of Fire. Next question is, how much is the Atlantic Ocean increasing every year? So we're going to look at the border between the South American Plate and the African Plate, and we've got little bitty arrows there, so that is less than 3 centimeters per year. What geologic features does plate tectonics help explain? We're looking at this image, and it's showing us a divergent ocean-ocean boundary. And each of these cylinders at the top is a core sample. So this boat that's going over is drilling into the earth and pulling up samples of the rock. And there's this strange phenomenon that you have more sediments and less basalt the further you get away from the ridge. So plate tectonics helps us understand how this works, because the seafloor is youngest near the ridge where it was just produced, and sediments thicken away from the ridge because age increases away from the ridge. It takes time for sediment to settle out of the ocean. Bits of sand and clay and mud and life forms settling out over time. So the longer the rock is there, the older the rock on the seafloor, the thicker the sediment is. Formation of linear island chains. So here we're looking at what is going on in Hawaii. And that is a linear island chain that's formed from a hotspot. So what is a hotspot? It is just a rising mantle plume. A rising mantle plume. So it's superheated mantle material that rises up in a big mass. Okay, when that happens, the magma chamber stays in the same place. The hot spot does not move, but the plates are constantly moving. So the plate moves over that hot spot. So we have the volcano forming over the hot spot, and the volcano doesn't move anywhere, but the plate moves. And so volcanism shuts off as the plate moves further away from the hot spot, and eventually, as those rocks are cooling and condensing, the plate subsides as it cools, and so islands become seamounts. Examples of linear island chains here. This is not in your notes, but just showing you the way that they work. We've got Hawaii, and we've got islands off the eastern coast of Africa. And in both cases, you can see that they're lining up. And that's the point here. They're not forming an arc like you would find with an ocean-ocean convergent boundary, but rather they are a straight line because the plate is moving directly over a hot spot. So how does plate tectonics affect a hot spot? It does not. The hot spot isn't going anywhere. The plate moves over the hot spot. Why is South America lopsided? What I'd like you to do in your notes is take a minute and write a paragraph, roughly 5 sentences, describing why South America is lopsided using the information you've learned about plate tectonics in your book. So what do I mean by lopsided? Why is one side higher than the other side? Okay, so in this case we can take a look. The brown is in the light tan. We're looking at higher elevations. Why is the west coast so much higher than the east coast? So you might want to pause the presentation, write down some of your thoughts, take a look at the book, see what you think, and try and make a sketch as well of what do you think this would look like, of a cross-section in between the west coast and the east coast. All right, now that you've written your explanation based on your knowledge and your research, and you've drawn your sketch of your cross-section, this is another way to look at the cross-section, and hopefully yours is going to be quite similar. So we've got our subduction zone that occurs as a result of spreading along the mid-ocean ridge in the Atlantic. So the spreading that occurs at the mid-ocean ridge in the Atlantic is moving the South American plate to the left. Okay, it's moving the whole thing westward to the left. And the eastern edge of the continent is not a plate boundary at all. And this is the key to understanding why the eastern edge does not have the high elevation that the west does. It is not an active boundary. We've got continental shelf, and this is a little trick to tell that there is no tectonic activity. When you have continental shelf, we know that there's no subduction zone there. It's not an active boundary. All right, so what is forming all of this high elevation in the Andes on the west coast of South America? Well, we've got subduction of the Pacific plate below the South American plate here, along the western edge. So as that oceanic plate is subducting, again, it generates magma by driving off water and lowering melting temperatures. So that creates this volcanic mountain belt all along the western edge there. And we get the Andes, these very high, very steep, volcanically active, dangerous mountains, and a very deep trench offshore, which often generates earthquakes so massive that it causes tsunamis. Evolution of South America. So just taking a look at how, on a geologic scale, things have changed so rapidly. So just 140 million years ago, and remember the Earth is 4.5 billion with a B, 4.5 billion years ago, the Earth was formed, and only 140 million years ago, we've got South America rifting away from Africa. In the late Mesozoic, 100 million years ago, we've already got a substantial size ocean there. The Atlantic is already looking pretty sizable. And now that movement has continued for over 140 million years. It continues to increase the size of the Atlantic Ocean. All right, putting all of these pieces together, I would like you to think about what would the safest place to live be on this map. So you've got this in your notes. Continent A is on the left, continent B is on the right. And I'd like for you to identify possible plate boundaries in this area and indicate whether the boundary is divergent, convergent, or transform. And so with that, where would you get earthquakes and volcanoes, and then determine where it is safest to live. And this is just for you. You're not going to turn this in, but it's still important for you to do the exercise to try and figure it out. Okay, some things that you should be looking for. If we look at the middle of the ocean, we can see this jagged zigzag pattern going down the ocean. So that tells me, aha, there's a mid-ocean ridge there. So I know that this ocean is growing. So you may find earthquakes there, but they won't be extremely strong. And there are volcanoes all along that boundary, but again, they're not very strong. So they won't pose much of a risk. If you look over to continent A, I see something kind of alarming. It's this deep trench, so I know there's subduction there. And I see very high mountains. So high mountains right near a subduction zone is a big red flag to me, because that tells me I've got volcanism going on here. And because it's a continent, I know it's probably explosive volcanism. Whereas if I look at continent B, I can see this light blue edging around continent B, which tells me it's tectonically inactive. It's not moving anywhere. It is stable. Okay, and so that tells me that it is a safe place to be.